I am the offering manager for the Redis enterprise solution on Linux on IBM Power hardware. Brad is a distinguished engineer and really a pioneer in the field of working with Redis Labs and other vendors on accelerator technology, well beyond just the flash RAM kind of mix that you've seen, but really this presentation will cover a technology called CAPI, which he's really a pioneer in the industry on, articulating the value of that and working with vendors like Redis. So I think you'll find that incredibly interesting, especially if you were at some of the sessions from Redis or Google that talked about some of the issues that we're all having with DRAM and Redis and larger memories, and now this CAPI solution is a really good alternative to some of the problems in that space. So we are going to co-present. However, if there's any questions, I'd like you to use two options. One is my email is on the presentation here. Contact me if there's any questions, and I'll work with my counterparts at Redis Labs on the solution. Or you can come and see us at the IBM setup over here. The third option is just stop by after the presentation. I'll give you my business card, and we can have a discussion after that, so multiple ways. These charts were posted a couple days ago on the Dropbox, so they're already out there. So everything's out there already. So one quick introduction. Brad is a distinguished engineer with IBM in the Power Systems brand, and he specialized in solutions and in the database field, and really a pioneer in the work of accelerator technology, and he'll take you through some of that. So Brad will start, and then he'll turn it back to me, and we'll kind of go back and forth on this a little bit. So
cool. Thanks, Chuck. So first quick question. How many people went to the 2 o'clock session where Chian talked about Flash and Redis? Okay, so I don't have to talk any about that, but that's really cool. But what he didn't mention, I gave him a hard time afterwards, was we've had this solution for a couple years now already on Power. So you don't have to wait for all the new memory to come out because some of that stuff exists today. And I have two goals for this presentation. Number one is hopefully you all learned something. And number two is hopefully I don't fall off the stage because I tend to wander when I present. And so I feel confined right now. So people always ask, if I push the right button, why did we get into running open source databases like Redis and some of the others on Power? Power's a business machine. Power runs relational databases, all that. Well, the reality is what we see happening is for people to actually get to the answers they want anymore, in business, they're using all kinds of data sources. They're analyzing stuff across all different types of data sources. And so to make the management of that data easier, we made sure that it was all available on one box. Okay? So we have clients that run Redis and some of the other open source databases on the same box that's running their Oracle or SAP or DB2 applications because it's easier for them to manage, and it's all right there. So from real-time decision making, it makes it a lot easier. You don't get all the networks involved. So that's why we do it. It's all about trying to provide better insights across vast and numerous sources of data. And that's why we got involved with these. And we talk about it in this way, you know, the modern data environment emerges, and it's been around in some sense, but people are just starting to see it, where data is coming in faster than they can handle it, so ingest becomes a problem. Sorting through it, cleansing it, making sure they get what they need, and in real time. And I always think it's funny, real time, not too long ago to some people was, hey, you know, I'm just going to do analytics across my data warehouse of what happened the last 6 months and use that to try and predict what's going to happen the next 3 or 6 months. Not quite real time, right? But that was real time for data analytics. Then it got to be, well, I got to get closer. Now people are making decisions on data basically in milliseconds. Okay, they're trying to see exactly what's happening to make the best decisions with the most up-to-date information as quickly as possible because it's important to their business and it becomes a real business advantage. Some of the financial institutions that we work with on Wall Street, one guy told me, you know, if you can give me 5 milliseconds faster than the guy across the street, it's worth $500 million a month to me. And I said, 10%? We'll make it happen for 10%. Well, we made it happen, but I didn't get 10%. But life goes on. So we're going to talk about why speed matters, and I kind of went through some of that. We'll talk about what we've been doing in the last few years with the Redis team and making sure that Redis as an available database, everybody talks about it. It's fast storage. We use it for caching, all kinds of things. We needed to keep it fast. But what we were trying to solve for commercial customers was scale. Right? Everybody knows scale becomes a problem when they get too big. I'm adding nodes, and I get some of the, even though it's weak consistency, some of that gets in the way. But the biggest issue was the more boxes I have, the more network links I have. And the number one failure issue in most data centers is the networking. So it was actually a reliability thing to cut down on issues. And we'll show you what we've done. So, Chuck?
One of the biggest complaints we get all the time is that people want larger DRAM, larger memory, and basically to fit the database in memory. And we in the industry have been pushing that, but as was explained many times during this conference, once you get up above a terabyte of DRAM, it starts to become expensive. So basically, we started working with a few vendors in the NoSQL space, Redis, Neo4j, and a couple others around this notion of extending DRAM at a lower near memory cost price point with additional types of technology, and that's what we'll talk about. So we were in 2014, 13 working closely with Redis on really solving this issue. Customers were having in-memory requirements greater than 1 terabyte. Now that's zooming up way higher than that. I've actually done POCs recently at 56 terabytes and then 40 terabytes for a defense agency just recently, with people even now talking about next year petabyte type requirements for data actually being in memory. So just a couple other things too is, in addition to this theme of data in memory and part of the solution being flash or near memory flash for a price performance standpoint, the CPU component, as we're finding, is also really important. So the data in memory is important during steady state, but the CPU component is also important because you're probably going to run applications on that server too. And then one of the things we found in some of the proof of concepts that I've worked on at the 40 terabyte and above range with these types of solutions, mixing Redis and other vendors with RAM and flash, is that data ingest, actually loading data into the database, both the first ingest and then the hot ingest, is also a big issue too to think about. So it's not only a steady state performance and price performance improvement that comes about from the result of augmenting your DRAM technology with flash technology, but it's also ingest. So keep your eye on the number of CPUs and the number of cores and the CPU performance as well, because some of the benchmark we've worked on, we thought the problem would be at 40 terabytes, the price performance curve and how that would work out with the combination of DRAM and flash. And the initial problem was just loading 40 terabytes of data into the database, and it took a lot longer than we thought, so we had to do a lot of work on the CPU and parallelization side of that as well. So one of the messages I just want to impart on this chart is that you're going to hear a lot about the mix of DRAM and flash at this conference, but also keep in mind that you do have to load the database into the system, and that often comes down to the number of threads per core, and it's a CPU issue, not only just a memory issue. So why speed matters, the story I tell is 20 years ago, I was a manager in a group and we were doing a home banking over the internet project where transactions would come in from Netscape browsers and come in through an IBM Power System and into a mainframe, and we were running that environment in production and people were doing home banking over the internet, and I was the manager of the group that kept that system up, and every day we would have a problem. And 90% of the problems were with database performance. It was, you could almost guess today's problem would be database performance, I/O performance, not enough memory, that kind of thing. So basically, these required DB access times for a single database, less than 1 millisecond to deliver the 100 millisecond round trip that everybody expects. And then add to that the fact that you have multiple database environments. So again, this is why the speed matters equation. And I would say from a practical perspective, from the year I spent working 90-hour weeks, why speed matters is also because 90% of the problem my team had, and this was pretty much 7 days a week, were in the database. And so anything that you can do to mitigate database issues in terms of technology will save you a lot of money on the agony or the people end of things. So consider that in addition to the pure mathematics here on why the speed matters to deliver that 100 millisecond transaction. This is also something we do a lot of work with Redis, but really from the people standpoint, the performance issues, like I said again the third time, is that most of the problems that we had in the production systems I'm used to happen to be within the database itself, and oftentimes involving storage people, and then you have two groups talking to each other, and many times people get a little bit defensive and that kind of thing. If you can mitigate a lot of this with flash and RAM type in-memory solutions, your life will be a lot better, and in the end it'll be a lot cheaper awful quickly for you. So we'll talk about the IBM Power Systems solutions for Redis Labs Enterprise Cluster. So just to differentiate, you can run Redis open source on Power hardware from IBM. It runs really well. We have many customers doing that, universities, large credit card companies, everybody's doing that. The step up from that is the commercial product, Redis Labs Enterprise Cluster from Redis Labs company here. About 50% of the customer engagements we deal with, so we have 180 engagements currently going on in my team right now across all the NoSQL vendors that we work with. And easily 90 of those 180 right up front will start with open source, and the other 90 will go immediately to the commercial, fully supported product set. So what we see in IBM and the enterprise customers, which may be different than what you are, is about a 50-50 base for the NoSQL space. People being very comfortable in some cases with the open source solution, in other cases don't want anything to do with that, want a fully supported commercial version, and they will start with that. I would say the prevailing interest being driven by, they just want to lower the cost of the software. That's straight up. And then the second thing is really the NoSQL space, where Redis Labs and such are in there, really viewed as a platform for innovation going forward. But really the primary reason when we survey our customers, when we survey our sellers, when we survey many of our partners, straight up lower cost to do business. Remove the software component of the IT equation to free up some additional capital to spend on innovative projects. So Brad will take over from here and take you through the IBM Power 8 technology. It's quite impressive, and he'll talk a little bit about the different elements of our leadership in processors, memory, cache, and data pipes and accelerators, both CAPI and a little bit about the NVIDIA NVLink technology that we also have on our system. But again, the theme I want to leave you with is a lot of times we talk a lot about data in memory and the value of that. But again, don't forget, especially in processes like data load, data ingest, and running applications on the same server as the database, you also need the heavy-duty CPU processing power.
So before you heard us talk about power, how many people in here understood what power technology was? A couple of hands. That's better than some cases at some of these conferences. So Power 8 was a big change in the power line. Power's been around for a while. But Power 8, when we first designed Power 8, we thought about it with data, big data, analytics kinds of problems. And so we designed the processor with that. That's why big analytics apps love threads. That's why you see 4x the amount of threads than you would see in an Intel processor, for example. And you can run this processor in one thread mode, SMT2, SMT4, or SMT8, all of those modes. And depending on the application, it'll run faster in one mode or the other. And it's not always 8, sometimes it's 4. It depends on the application you're running. Memory bandwidth, as a processor designer, the thing I hated most was after you spent your life for months designing a processor to get the fastest cycle time you could, to see a performance run and recognize that a third of the cycles were idle cycles waiting for memory, waiting for data to get there to be processed, right? It's like having a car with good fuel economy, but you leave it running in your garage at night for some reason, right? You just don't get the advantage out of it. Well, we spent a lot of time on memory bandwidth. We actually changed the way we were going to memory and run in 2 different modes where we have what we call a split memory controller on Power 8. In the past, the memory controller was in the processor. It was a separate chip. It was in the processor. It bounced back and forth for years and years. We actually have a split design. The reason for the split design was twofold. Number one was bandwidth. We can drive a lot more bandwidth, and it added an additional layer of cache. The second reason is, For years, we kept hearing about new memory technology, and it wasn't quite ready. It's 2 years down the road. Oh, wait, it's still 2 years down the road. We really felt they were going to happen soon. And we didn't want to have to spin a processor to put new memory technology on, whether it be bubble or resistive or all the different memory technologies, 3D, cross-point, whatever. With that design, we don't have to change the processor to put new memory technology on this part. Okay? We're set up, and I can tell you that every one of the major memory vendors, which there's really only 4 today, have PowerAid parts strictly for one reason. We allowed them to put a controller on that could put memory in there without having huge delays because, oh, there's really a memory controller in the processor, now I have to do another one, and mate them. They mate to the half design that we have, and they use a card that we gave them, and they're all testing these new memory technologies with a real processor at speed, which they really love to wring out the memory. But bandwidth is a big deal. The cache size, as I remember, just within the processor core, 4x the amount of cache over an x86 part, also an additional layer of cache in the memory controller, and then the bandwidth on the bus. A couple things that we've done. Besides the fact that we're running PCI Gen 4, which everybody is right now, and the next part is Gen 5, we created really 2 additional buses, 2 modes, I'll say. Number one is CAPI. CAPI just stands for Coherent Memory, a Coherent Accelerated Processor Interface. And I'll show you what that does. When you think about, hey, I'm talking to an SSD, and then I'm using NVMe to talk to an SSD, and now I can use CAPI, we reduce the overhead and increase the throughput. And I'll show you some comparisons. The other link that was put on there is what gets referred to as NVLink, and it is a direct connection to GPUs, NVIDIA GPUs. Again, the biggest problem with accelerators and things that people were trying to use was I had a really fast processor and it could really do things with memory and data, and I had this accelerator on this side, it could really do things fast. Unfortunately, they had to talk together and they had to talk through a straw called the PCI bus. So while they could talk terabytes per second, the PCI bus was sitting there around 16 gigabits per second. Okay, so I was always waiting to move things. We got rid of that with the idea of CAPI because we put the accelerator and the processor in the same memory space. We keep them coherent. And we'll show you what that means performance-wise in a little bit. So the reason we did that is, well, people have talked about Moore's law, it's slowly dying, whatever you want to call it. But the reality is we've gotten so close to the edge of physics in the current silicon technology. When we did a processor spin at the P6 time frame, the cost to build the new fab to do the shrink of that technology was about $200 million. And we could do the spin fast, and we got about a 40% performance increase by making the chips smaller with the new fab. The last technology spin that occurred, it cost about $2.3 billion to build the new fabs. That's why they take longer to happen. And we only got about a 15% performance improvement in the shrink. So basically what's happened is, Einstein did a lot of great things around physics, but he didn't teach us how to get around the physics of silicon. And basically, we haven't figured out how to make some of the insulators any thinner than an atom. If anybody has a good plan to do that and control the fission that occurs when you make it less than an atom, we can all make a lot of money. But that's basically where we are in technology. And while there are other technologies that allow us to get smaller and faster, none of them are cost competitive today. They're very, very expensive. So gallium arsenide, graphene, all the different elements that we're trying to use, we can make them, but you couldn't afford the parts to do it. The parts are astronomical cost of manufacturing. So we did this work on accelerators to make accelerators faster and more efficient use in the systems. That's how we can get price performance. And basically all it does is inside the power processor we have what's called the cap unit. And what it does is we took some knowledge that we had from building big SMPs and how to keep them coherent, and we applied it to a bus. And so we do memory coherency across them. They're in the same address space, which means I get rid of a lot of the overhead of trying to do I/O, which is fairly significant. To do, this was all measured using Linux. It costs in excess of 20,000 instructions, and in some versions we've seen it go up to as high as 27,000 instructions to do an I/O cycle, to actually do a read and a write, because I have to do address translation, I have to pin buffers, I have to do all this overhead before I can actually kick off the DMA and move the data. With CAPI and the coherent attach, I don't have to do all that work. I just have to have an API to do it, and I can do that work. We're actually under 2,000 instructions. This is a little older chart, to do that transfer. Besides giving you more bandwidth, it also says, we just gave you in excess of 20,000 instructions to do compute. So you can actually do more compute in the box than you could before because you're doing less overhead tasks in the box, and you're using your cycles to really process data and process things you need to do as opposed to just moving data around. So just to give you an example, what I have here is the same exact comparison on the same hardware, doing traditional I/O with the file system there, with a block device, direct attach I/O, NVMe, and CAPI. And you'll see what happens is the number of instructions come down dramatically that I need to do, so less than 25% of the instructions, but it means I get a 3.7x bandwidth improvement. I can move much more data in that period of time. So some people would say, hey, I get more bandwidth at less cost. Usually I don't get both positives in one thing. Usually there's some other game. But the reality is we've done these measurements several times with different things. And this is where we saw the advantage in being able to extend now and take things like Redis and other in-memory databases that we could scale them. Because now we had efficiencies down in the range that allowed us to treat block storage as an extension of RAM. Okay? Now I still don't call it memory, because to me memory is byte addressable, and we just said block storage, right? But there's an interaction there. But the reality is this storage now that's out on the flash, whether it be the internal card or an external flash array, is under the control of the application, directly under the control of the application. So they can organize it the way they want to. They can do other efficiencies. And we've seen some of the databases that are using this make other advances in efficiency because now they don't have to worry about somebody else messing around with their data and reorganizing it. We have two versions of this that's on here. One version actually is a CAPI card with fiber channel out the back end that can talk to an external array. So you can actually, in a 2U box with an external array, have a database that's 57 terabytes. If you have a database that big, we should talk, because you have other problems if you have a database that big. But you can put multiple out there. And then we have a card that sits in the system just like an NVMe card, but it's CAPI attached. So you get the advantages of CAPI with an internal, and it's a 2 terabyte card. So that's how we're leveraging things with Redis to extend their memory. So that kind of gives you a bit about the technology that we've put in here, how we're leveraging it. What I will tell you is that right now, Power 9 is getting ready to come out. These buses actually get even faster. And things that we're doing, as I said, PCI Gen 4 goes to PCI Gen 5. We're also doing, as part of the Open Power Foundation, which was another big thing with Power 8, I'm doing a thing called Open CAPI, where we will be running the CAPI protocol over an 80 gigabyte bus that's attached. So bandwidth in the system and latency to get to this block storage is not going to be a problem for the applications you want to run. And because we save you all those cycles, you'll be able to use this bandwidth effectively to make your applications run in the environment with very low overhead in the system. So that's the technology. Any immediate questions that anybody has? Otherwise, I'll turn it over to Chuck to talk more about the Redis relationship that we have. No? All right. They're going to build the questions for the end.
All right.
I can see it.
Okay, so just a couple words. What actually is CAPI, the manifestation of CAPI? So actually you would purchase a Power 8 processor from IBM. You would pick the amount of terabytes or gigabytes of RAM that you want from us. Typical purchase price for one system, $15,000 to $20,000. And then if you need and want CAPI, it's a card. I purchased that for around $6,000 or $7,000 per card. The card comes with two things, an FPGA that you can use to accelerate 1 to n algorithms in, and 2 additional terabytes of near-term memory or NVMe type memory per card. You can have, depending on the model that you choose, between 1 and 4 CAPI cards per system internal, and then there's an external variant that will give you a total of up to 56 terabytes of that. All can be exploited at with Redis Enterprise Cluster. The code that exploits this comes from Redis, so when you get Redis Labs Enterprise Cluster, the version for Linux on Power with the CAPI support. We have tested this at max capacity, 56 terabytes with a large credit card company. You probably have the product in your wallet. It works really, really well. And so that's basically an overview of what is CAPI. So CAPI is a protocol, but at the end of the day, CAPI is a card. And it's 2 variants, like Brad said, the CAPI internal cards, 1 to 4 cards, plug into the PCI slot of your IBM Open Power servers, a couple $1,000s each. Each of them gives you additional 2 terabytes of memory and an FPGA. We co-developed that with Xilinx, is the company. There's an external version that then allows you to connect either a flash system 900 or an 800 from IBM if you so choose to do that. If you need in excess of 9 terabytes total memory, then you would look at the CAPI external solution to go up to 56 per system. We have reference architectures for both of these configurations. And again, so how would you get this, or how would you realize this? You would get the code from Redis Labs, and you would get the hardware from IBM, including the CAPI card from IBM. If you're interested in this, we run proof of concepts all the time for no charge with our customers. If you have an opportunity and you want to talk to us, we can set up an environment in our labs in the US or in Europe, or you can dial into them. We can have our experts work with your experts, load your data into it, set up the secure access, and you can do your testing of your workload with your data the way you want to do it on our Power 8 system with Redis Labs, with CAPI, and take weeks or whatever and figure out what the results are for you in your environment versus some of the stuff I'll show you. And we do this all the time with our different clients. We have our architects and stuff that do this kind of thing. So again, the flash system for greater than 9 terabyte Redis databases that you want to utilize the flash technology for, the IBM Flash System 900.
Chuck, just let me throw in one thing, right? The customers that we have are attaching multiple nodes to a Flash System 900. So it's very hard to imagine for some people a 57 terabyte database. But if you have 3 or 4, 8 or 10 terabyte databases, they all fit in that flash. And that flash array has 16 ports to it, right? So you can attach and get redundancy and all those things that you'd normally do to make sure you have connectivity with one flash array. I know we just showed one there, but that's not the typical environment that we see. It's multiple nodes attached to it.
So a couple things on the performance. So the IBM Flash System 900 itself delivers 100 microsecond response time at 1.1 million I/O per second. That's super impressive. But if you go back to that chart Brad showed and he talked about CAPI, one thing on there is you can see that also that environment at greater than 1 million I/O per second, you're also saving between 20 to 30 cores of CPU based on the reduction in I/O path length from 25 to 27,000 per instruction in the Linux kernel to the 2,000 with the CAPI. So in addition to freeing up CPU and having that impressive microsecond response time at that really high I/O per second, the bill for your software may significantly go down if the vendor you work with charges by core, which many of them do. So multiple benefits across the board for utilizing this technology. In addition to just the performance itself, reduction in, I'll show you some reduction in hardware costs, but also reduction in software costs. And then once things are on flash and with larger memory, you have really the big thing is less problems with your database. And that can be a big thing. So today in NoSQL on x86, you have a lot of problems with a lot of scale-out systems, typically relatively smaller amounts of RAM, that kind of thing. So you want to have that differentiated on a more of a condensed Power 8 server environment, up to 56 terabytes for NoSQL-based applications with the CAPI, reduction in CPU path length, flash technology to accelerate your I/O, both your reads and writes, and then also the reduction in software cost and reduction in DBA, crit sits, and overall anxiety in better performing systems. 192 threads in a 2U server draw is attractive in the case of database ingest, both initial ingest and hot loading of data. And we see this consistently in proof of concepts that we run with customers. They think they're going to come in to an IBM lab and load in 10 terabytes of data, and it's going to run in an hour, and we're going to be up and running and that kind of thing. And this is often the first surprise that we hit, is that you really need that multi-threading during the actual loading of data, and then the hot ingest phase when you want to load more data into the database also can really take advantage of a lot of the multi-threaded environment of this kind of thing. So basically what we see is in some of the cases with IBM, our design point for NoSQL non-accelerated environments on hardware was we like to deliver hardware that runs at a price performance level, the NoSQL databases, be it Redis, be it MongoDB, be it Neo4j or Cassandra, at least twice better price performance than an Intel system, because we figure unless it's 2x better, nobody will even look at it. The interesting thing is in the accelerated database space, we get a lot better than that, and I'll show you some other examples of that. Really a lot better than 2x. So rather than do a 2x price performance guarantee, we really expect 3x and above in many cases, benefits with the Power 8 technology for some of these environments in the NoSQL space versus the x86 space. So reduction in physical infrastructure, price performance reduction, a lot less energy footprint, a lot less rack space, and really capability to do things with 56 terabytes of extended memory that you didn't have in the past. And in particular, in the high-end financial services space and in the defense industry, this is something that's a real differentiator for certain really large database environments. So this is one example. I want to point out two things on this. You get the standard IBM Power 8 versus an x86 system. In this case, it came from Dell. And then our price performance for the same Redis enterprise workload was more attractive. But the key thing I want to show in this chart is that one of our systems is $17,515. I think probably in your mind you hear IBM and you think $300,000. Our open power systems are really fast at the $17,000 price point. So this is one example of a benchmark where we had a 67% throughput gain and a cost savings of 54% compared to Dell. This is a pure without flash scenario, so straight up without flash versus without flash. So the message on this chart is our hardware is cost competitive at the $17,000 price point with a Dell PowerEdge type environment. This next one is with flash. So again, the IBM Power 8 with CAPI versus the Dell with the NVMe flash. And again, now we get up to the 2x performance and the 70% cost savings. This is another interesting one. This is an actual university research with Redis on flash versus Redis on RAM. And again, significantly improved price performance with the Redis on flash Power 8 savings. One thing I want to mention, in some of the sessions I was at earlier in the afternoon, they talked about the one-year cost of a Redis environment on Amazon or on some other cloud providers being hundreds of thousands or millions of dollars. If you go back to this chart here, and you can look at some of that on-prem price point, and that system is for amortized over 3 years. So 23,000 divided by 3, being significantly faster than some of these really large bills that you're going to get in the cloud environment. Maybe something to think about, although there may be some other reasons you don't want to do that. So we have a reference architecture for Redis with CAPI on Power 8. It's called the Data Engine for NoSQL. And it's just a complete reference architecture on everything you need for the internal Cappy Flash or the external Cappy Flash environment. In addition to that, any engagement that we enter into with you, you'll have an IBM architect assigned with you, and then you'll have the ability to do free proof of concepts with us. On our hardware, we'll set it up, you run your workload, give it a try with your workload. So you get your numbers. You know, for all these IBM numbers may not be what you get, so we're going to offer for no charge that you can run your workloads, your data, the way you want to run it on our Power 8 system with our Cappy, with our architects to help your people. And then you get the results that, you know, are for your environment, for your use cases, for your workloads, for the conditions that you want to run it in at the price points you want to explore with us. No charge. Typically, these benchmarks or these proof of concepts, we like to plan for a couple weeks. Usually we'll say 2 to 4 weeks. A lot of times we'll go week 5 and 6 because the team wants to explore a few other scenarios. But typically they're about a month in duration, and almost all of them are remote dial-in. You guys just dial into our system, and while you guys are loading your data, we have people that, you know, work with you. And typically we'll set up a Slack channel, and we'll have like your company and our company Slack channel where we communicate with each other and have calls and all that kind of thing. We'll have a project manager that'll be assigned to it and work with you on that kind of stuff. And then Redis Labs would also help out with that too. So here's a cloud scenario, 800 plus databases on a single P8 box. We just announced last Tuesday out here in San Francisco a new database as a service offering for developers for cloud, where you can have Redis open source software and a number of open source vendors. And again, a couple hundred different Redis Labs instances on Power 8 on a relatively inexpensive box if you want to look at that. You can use either VM technology or Docker container technology or even bare metal if you wanted to, but any of those delivery mechanisms for cloud would be quite okay with us. So Brad, do you want to do this one, or you can?
Sure.
Okay.
So Chuck mentioned, you know, the open source databases and database as a service. You can put any of these open source databases that are support on Power, and there's several. I don't know if you have a list in this chart deck, but you've mentioned several of them: Cassandra, Neo, Mongo, Redis, of course, several others. And we have tools to help you do simple installations. So you can tell it how big database, and it'll go out and create them for you on a 1.1 basis. But we also have a couple database as a services that we've done. An open source one being an open platform. It's all open source code. It leverages some of the Trove technology within OpenStack and has that user portal. We created an updated user portal, self-service portal, and we have some big companies that are using this because their development teams want to use these different databases initially in dev test and then in production. And the developers didn't like the fact that, hey, I want a Redis database, and the IT department would tell them, okay, we'll go and get the equipment and set it up. We'll have it for you in 3 to 6 months. They want it right away, and with this service, you can get them set up depending on the size, between minutes and hours. The last one is another software offering that builds on top of the open source stuff, but it'll do a lot more. It'll allow you to have the licensed databases. It'll allow a whole bunch of other things. It's a full cloud management system. So we have some service providers that are leveraging this, and they have more than just open source databases. They manage a whole bunch of applications on their cloud environment through this code, and they have a database as a service plugin that goes into it. So they get the self-service portal to do the same thing as before, but we can do other databases because besides leveraging Trove, we leverage some scripting technology, and we can do a bunch of different things. So it's just 3 different ways of deploying the open source databases on Power that exist. Resources, you know, Chuck mentioned you can send him an email. I always put his email up there, but you can contact me as well, but Chuck always finds me. And then you have the different portals down bottom that you can go and get additional information about running Redis on top of Power. So I think that's pretty much
I would just say
the last charts. Some more things, and as Chuck said, these charts will be posted.
Yeah,
they're out there, and then you'll have all these links, so you don't have to be scribbling to try and write them down, or seeing if your camera focused well enough that you can get the right digits in there. So I think that's it.
Yeah, I think, just a couple things. Number one is come and see us if there's more interest. Connect with me on LinkedIn. Chuck Calio on LinkedIn, Chuck Calio IBM. You have my IBM email, ccalio@us.ibm.com. We work really closely with Redis Labs. If you're interested in more, our typical progression cycle is we'll have a discussion with you, an IBM rep. We have an architect who can have a discussion with you. Free, no charge proof of concept. You don't have to believe any of the performance data that we showed from IBM benchmarks. We'll work with you for free. You can dial into our Power 8 environment with our CAPI and our Redis Labs software and our experts, and we will do a proof of concept with your workload, your use cases under your conditions, with the configuration that you tell us you want to run with, the amount of money you want to spend on the hardware. We'll do that with you, no charge. We like to try and cap that exercise at 4 weeks. Sometimes we go to 6 weeks. So we'll do an architectural reference with you. We'll work on any other kind of stuff you want to do, and very, very flexible and a very efficient team that knows how to do those proof of concepts. And again, we find that very useful in the sales progression cycle because your use cases are probably, in some cases unique. And oftentimes, just in closing, before we open it up for questions, the big thing that we find as a surprise is that you really have to examine the full life cycle of the database: loading, ingest, hot loading, steady state, different types of environments, workloads, and use cases, and then see what works and see what didn't work. So don't forget, in a proof of concept, some things won't work like we thought they would. There may have to be some code changes made, or there may have to be some configuration adjustments made. So typically these engagements that we work on with clients do uncover some things that were not something we thought about at the start of things, but it's good to do that. And again, I think it's a powerful tool to progress the sales cycle beyond opportunity identification towards opportunity management and really see if this is of value to you. So let's open it up for questions here.
I'm dying to throw this at somebody. No. Questions? No questions? Is everybody still awake?
Okay, I think you saw the drinks getting set up outside.
Yeah, everybody's looking for the bar.
There's one, Brad, over.
What is the next generation of Power 9, for example, coming out?
Yeah.
Power 9 will be out in limited availability yet this year. It's being brought up in the lab. It's kind of a fun experience right now because it's the first time we've ever brought up a processor where there's multiple companies next to each other in the lab. So there are IBM, Google, and Rackspace engineers bringing up different systems in the lab right now and doing final tweaks. So those boxes will be out sometime later this year, and a bunch of them will be being installed at the federal government because of the big Coral bids. We're building big supercomputers out of them for the federal government.
Compared with the Power 8, are they going to be more expensive?
I honestly can't answer that question. I'm an engineer, and every time I try and talk prices, the salespeople go and slap me upside the head because the biggest problem is I can quote you what the list prices are, but every customer has a different discount rate. And so I'm never right, no matter what I say.
You know, the question to that.
Yeah, I know the, just from the CAPI standpoint, so that's what I'm involved in,
Yeah.
the CAPI on Power 8 card is approximately $7,000 to $8,000. And generally speaking with Power 9, we're trying to get in at half of that with the same speeds and fees and that kind of thing. And then the current plan is to announce Power 9 in October. Not exactly sure how we're going to do that in New York, wherever. And then, like Brad was saying, the first set of customers will take a fairly significant amount of capacity, and very large customers, the Googles and the other federal government bids in the December timeframe. If you are interested in being an ESP customer of Power 9, send me an email because we could probably entertain that under the right conditions. If you would be willing to get up on stage with us and that kind of thing, we would always look at that, but the spaces are really limited. And pretty much the first 50 or something thousand units are pretty much spoken for. So it's kind of one of these things. So announce October, general availability December, but pretty much already sold out
For a little while.
for this year. So you'd be looking at acquiring something in first quarter because the first 50 to 100,000 of them are pretty much.
Right. And Power 9 has some changes in it, you know, mostly around those same bandwidth things that we talked about, faster buses. The internal bus on the processor almost doubles. So each core on that processor chip, and because there's multiple cores, but each core can handle over 7 terabytes of data per second, which is a kind of an unseen number. But we know there are applications that are going to use a lot of it. But it's really a phenomenal set of changes. And part of that was because of our partnerships. As I mentioned before, you know, Power 8 was the first what we call open power processor, where we have the Open Power Foundation. So there's 300 plus. I don't know the exact number anymore because every time I look at it, it's changed dramatically, that are working on that processor part. It's not just IBM. We have a big partner group doing that. And that CAPI bus that I told you about has its own foundation called Open CAPI that has many companies that you would recognize if we went through the names, helping work and planning to use that bus in future products that they're working on, different accelerators and different functions. So for us in Power, it's been a very interesting couple of years as we've gotten into open power. But we've seen a lot of benefits that we can bring to our customers for it. So it's been fun.
Yeah, I would say, you know, one other dynamic that we're seeing just in closing is that many of our customers, in addition to NoSQL databases, are interested in machine learning and deep learning and exploring that. So we're seeing this new sort of compute paradigm emerge where the AI, the ML, and the DL projects are running on GPU accelerated platforms. They do use general purpose processors for the data wrangling, for the model training in some cases. And they're also very interested in FPGAs and CAPI for other type of use cases. So really a lot of the action in hardware now is workload and use case specific and oftentimes involves accelerator technology, not just GPUs, and used in combination with both. Our model in IBM is a hybrid model, general purpose processors and accelerators. And some of the work Brad did with his team, state-of-the-art in CAPI, close partnership with NVIDIA, other accelerators, networking domain on the horizon, but continuing to innovate and being superior and also the CPU. We don't just believe one platform like a GPU-only computer is going to do everything for everybody. So we still have a sort of a really enterprise approach to computing that integrates AI. And then AI tends to feed off and drive more demand for NoSQL databases. And then the more data you have in your NoSQL databases, the better trained your ML and DL models will be. And about 80% of the time we see in AI projects, both machine learning and deep learning, involve data preparation and data phase. So it's really a surprising statistic that we thought most of the time in the project for a lot of the machine learning and deep learning experimentation going on would be in actually AI environment, but it's really in the data preparation and data wrangling kind of thing. So.
And we'll see a lot of other breakthroughs. One of the interesting things, at least for us, is our solutions aren't just going to support businesses anymore, although I love businesses and the financial guy, if I could have got maybe 5%, 10%. But an example that I think is interesting is we did work with a company in Europe, in the UK, on genome processing, and what 2 years ago took 9 months, they were able to get down through certain things that they were doing down to about 24 days. We now do it in 12 minutes. Okay, so we can process the full genome using an accelerator on a power system, on a Power 8 system in 12 minutes, which if you're the patient, not having to wait 9 months for a result, if it could be something that you want to treat right away, is really interesting. Another example, again from the medical field, how many people here have heard of proton beam treatments for cancer? When a patient goes into a proton beam, and this one just happened by accident because of a Mayo Clinic is in Rochester, Minnesota, which is where I live, and of course, we talk to people, and we found that the biggest problem they had with proton beam treatments was when they put a patient in, it's so focused, they don't always get the alignment right. So they'll take a patient out, they'll do this analysis and say, oh, wait, we got to put him back in because we have to realign this, because it takes them about 8 hours to process the data to know that the beam wasn't exactly pointed in the exact right spot. Now, of course, the problem with that is not only does the patient have to come back the next day to do it, they have to make sure they get him in the exact same position because they just moved him. And if they don't do that right, through some acceleration, they got it down to 8 minutes, and you can actually stay in the setup for 8 minutes. So not only do they make it happen faster, they make it happen more accurate and get a lot of the error things out of the way because of some stuff with acceleration. So I'm really cool on some of the acceleration stuff because there's just so many things that we're finding that because we made acceleration opportunities so much more efficient and usable, that there's so many things that are popping up all over the world. And that's why we have over 300 partners in the Open Power Foundation, is one of the reasons, I'll say. A lot of researchers, a lot of companies that are very focused on specific apps. So it's kind of cool. It's nice to go to my oncology doctor who's a friend and say, hey, we're helping you. We're helping you help patients as opposed to just helping people make more money. So it's kind of a cool feeling.
Thank you.